All right, welcome everyone. Today we're going to be going over trees and graphs. Trees and graphs are actually probably my favorite chapter in here, but it's also one of the longest chapters in here. So I might break this up over 2 days. Today we're going to go over trees and recursing down them. Tomorrow we'll probably go over graphs. Either way, there's a few things about it. One is that for trees, building them and graphs, you got to build them up, right, in order to represent them. And that could be a little tough. A lot of times in the interview questions, maybe they'll give you a tree, or maybe you'll be working on an actual tree, like the abstract syntax tree or the DOM. Those are some famous trees that we use every day. In fact, abstract syntax trees, you don't necessarily use them every day, but your tooling might as a developer. It's how a lot of syntax highlighting works, as well as refactoring or ESLint rules, so on and so forth. So we're going to dive into that. And so just today we'll be doing trees. We'll also go over binary trees versus normal trees, how to traverse down trees. You have in-order traversal, pre-order traversal, post-order traversal. I'm looking at my book. That's how I know those things off the top of my head. You have other trees like a prefix tree, also known as a trie, I think. I don't know how to pronounce that. And that can be very useful for things like autocomplete, which is a really interesting use of a tree, but I typically don't get asked questions involving that. And then tomorrow we'll get into graphs, and so we just won't deal with that today. When we dive into graphs, we'll have depth first search and breadth first search, which are two extremely important algorithms to have down. So we're going to do trees, and then we're going to do tree problems in the back, and then tomorrow we'll do graphs and graph problems in the back. Now a tree is a type of graph, so don't get too mixed up there with it. It's just that it's directed. So let's make a tree to demonstrate what that means. I'm going to go ahead and share my screen. Second, let me make sure. Yeah. Let me go ahead and share. Cool. All right, so for a tree, basically the idea is that you have a series, you have nodes, and then there's a root node, and then the child nodes, and that recurses all the way down. Now, the child nodes can either refer to their parent or their immediate child. They can't reach out across the tree and reference something else in that tree. As soon as it does that, it's just a graph. Maybe I should visualize this first instead. Let me do that. There. Stop share there. Bring this up. Okay, new page and cool. Trust. All right. 1 second. And interesting, it's not sharing. Let me do that a little better then. Oh, it said via cable. This is via AirPlay. They switched up my boxes. 1 second. Cool. Okay, so a tree looks like this. You have a node, and then let's say you have its children, also known as leaves. And right now, this is a binary tree because it has two ancestors. This one has two children, or sorry, not ancestors, two children. And if I kept going on, then this is how it would look for a binary tree, right? You would basically just have every node that has children can only have a max of two. They can have one, they can have none, but the max they can have is two. And there are a lot of common problems with this. Now, if you go down this tree and you're trying to search for something, then you would have, if it's sorted properly, you would have a big O of n log n time finding it. Or I'm sorry, not n log n, just straight up log n. Why is that? Well, because take a look. If you go left, then you immediately cut out half the tree. You go right, then you cut out another half, and then you're just left with, and then you go here, and then you've cut out that. And that only took 4 steps. However, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes here, I think. And that has a lot of them have been avoided just due to the nature of these types of trees. Binary search does a very similar thing, and you'll see the similarities when you start diving into that. Now, it's no longer a binary tree when you start having multiple children per node, right? And that's okay. It's not like, there's certain properties of a binary tree that make them very nice algorithmically, but when it comes to these other trees, you don't have to have that, right? And sometimes when you're building a tree in the real world, it's just to represent something in the real world. And real world things aren't necessarily binary trees, right? And so these are what different trees look like. And the main property, like I said, as soon as you have a node that references something other than its parent, it turns into a graph. So this connection here, oh, can't see it. Hang on. Let me refresh that. Screen mirror is not working. One sec. There we go. Cool. All right. As soon as, oh no, it's totally broken. Stop the share screen. Whew. Unable to connect. I'm so sorry. My iPad can't connect right now for some reason. Anyway, so as soon as, but all that was to say, as soon as it references something other than its immediate parent or its immediate children, then it's no longer a tree. All right, so let's go ahead and make one in JavaScript. All right, I'm going to show my desktop. Now we're going to dive into the code. So how do you represent it? Well, a tree is basically a collection of nodes. So a lot of the time, we're going to just work with nodes. And we kind of did that earlier with our linked list, right? And it's kind of the same thing, right? They have a value. You can give them a name if you want. I guess we'll go with value here, and then this dot value equals value, right? And then it'll also have children, so this dot children equals an array. And when you add a child, it's just going to be a node. So it's this dot children is a type node. It carries nodes, right? Very straightforward. So what might that look like? So let's say a equals new node 1, a dot children dot push new node 2. Oh, sorry. Node 3, new node 4. Cool. And now A has these children, and they're represented as nodes. And those nodes can have children, and they have values. And you can add whatever you want to these trees, in terms of data, especially in the real world. But this is a really simple one for us. Now, how do we represent a binary tree? Well, you kind of want that limit, right? So if you're doing like class binary node, I guess, you could do something where in the constructor, right, you still have that value, but you can have this dot value equals value, and then how does it do that? Stop doing that. Thank you. And then this dot left equals undefined, right, or something, and then this dot right maybe also equals undefined, and then you're saying A equals new binary node 1. A dot left equals new binary node 2, and then A dot right equals new binary node 3, right? And so A is now this is this, well, this forms a binary tree, essentially, right? So that's one way to do it. It's not the only way to do it, but it is one way to do it. Now, in the book, she also goes an extra step sometimes, says class tree, and you can do something where it's like structure. You have a root node, and you say this root, it's root, and if you do that, then D equals new tree and set it to A, right? So now B's root is this binary node, right? Pretty cool, right? And that's your tree. You're welcome to do that. Sometimes you don't have to do that at all. Frankly, for this, we're just here to set up a tree to help us do the problems. So that's why we're doing it. So there's one more thing to mention, and that's the difference between a binary tree and a binary search tree. So with and the difference is the sort ordering. So let me see if my iPad will work this time. 1 second. This is kind of hard to not visualize. All right. Cool. There, now you can see it. So when we have a binary tree, it doesn't matter, what goes in these nodes at all, right? It could be anything. We're going to stop at this, right? The value here could be like 1, this could be 2, this could be 7, 10, 12 is over here, 3, 5, who cares, right? And there's no rhyme or reason to why any of these nodes have a certain value. And that makes it a binary tree, right? But a binary search tree is important. It has an important quality to it. That quality is that the numbers are in a certain order. So what's that order? Well, the order is like this. Say this is the number 10, right? Anything on the left side, anything less than 10 goes in this side. Anything greater than 10 goes on this side, right? But that applies to the node below it as well. So let's say we make this one, let's make it a 5, right? We make it a 5. And now the thing is that anything on the right side has to be greater than 5. Anything on the left side has to be less than 5. But it has to be greater than 5, but also less than 10. That still counts, still matters. So we're going to have that. This might be the number 7, and this might be the number 3, right? But you're saying, well, Jay, wouldn't 7 go here? And maybe it does. Maybe it could when you're building it out, right? But if so, it'd be like 7, and then we'd have to put 5 down here. And then we'd have these 2 nodes again, and 3 would have to go here, right? Just to keep the property alive. This could be something like 8, maybe. This could be something like 6, and so on and so forth. But to keep it a binary search tree, you have to have it in this order. Why is that? Well, let's say we're trying to find the number 6, right? Now, in a non-sorted, and just a regular binary tree, that 6 could be anywhere. You'd have to find it. Maybe it's over here. Maybe it's over here, right? You have no idea where it's at, right? But in a binary search tree, it kind of follows the concept of binary search, where you choose one side and you know that that side's going to get you closer to what you're looking for. What does that look like? Well, let's say the search parameter is 6. And we start at the root. Well, we say, okay, well, 6 is less than 10, so we choose the left side, right? Because we know everything on the left is going to be less than the number that we're looking at here. Let me change the color. And so we're at 7. Now 6 is less than 7, so we're going to go to the left again. And now we're looking at 5. Well, 6 is greater than 5, so we're going to go to the right. And look at that, we found 6. It's right here, right? So that's the thing. You know to go left or right based on whether it's less than or greater than the number that you were looking at. And that gives you some really nice search features. That gives you the log n, O of log n that we're talking about earlier, which is basically binary search. This is kind of the flow of binary search right here that we just went through, right? So that's why that's important, right? So keep it in mind when you're coming across the questions. And we're going to, what's the next one here? I deleted the 5, but that's okay. So there's that. Then there's talking about balanced versus unbalanced trees. This is kind of an unbalanced tree right here, as it is. It doesn't matter if it's a binary tree or what, but you could tell that the left side is a lot bigger than the right side. And that means that, when you search over here, it's going to take a lot longer than when you search over here. And that's the worry about balance. Now, you probably won't have to worry about balance too much during an interview, but there are a few questions and there are some more advanced algorithms. So if you're doing some more advanced backend work, you might want to study those. You also have incomplete binary trees and complete binary trees. I haven't been asked too much about that. I'm reading through the book right now. Perfect binary trees, full binary trees, cool. Binary tree traversal. This is something you need to be comfortable doing. And this is going to be one of the tougher things. If you've never done this before, this is going to be one of the tougher things to figure out. And that is, how do we traverse or go down, another way to put it, how do we go down this tree? And it doesn't have to be a binary search tree. Let's make it like not a binary search tree, right? Cool. Just put a bunch of random numbers in. And now we need to traverse down this tree. And that has its own sort of, there are a few ways of doing it, right? And the different ways of doing it are more like, well, when do you pay attention to the value? So let's go by going over it, right? So first we have in order traversal. And the idea of in order traversal is that you visit the left branch, then the current node, and finally the right branch. What did I just say? So what that means is you go to, so in order traversal, let's take a look at the function, right? So this is going to be sort of a recursive function. So this is going to be a little confusing. Node, right? First step, we're going to, if not node, right? We're going to visit, oh, I'm sorry, we're going to in order traversal on the left. Node.left. And let's pause right here. There's more to the function, but let's talk about what this is going to do to our program flow. Basically, it's going to start at 10. So take a look at the tree up here, 10. And then let's say we say in order traversal node. Well, it's going to be like, okay, well, we're calling that function again. So let's call it again. And we're back up here in order traversal node. Now we're at 7 because we went to node.left. And then if not node, yep, there's a node there. So we're going to do this. We're going to in order traversal node.left, and it's going to go down here. And then we're like, okay, cool. Well, now we're here with a new node. I'm going to change the colors to make that a little more obvious. We're back here again. Say, oh, okay, we go to the left. All right, cool. There we go. Now we're here again. We're like, okay, well, let's do it another time. And boom, there we go. And then we're back here again. I'm running out of colors. And there isn't a node on the left. Or no, I'm sorry. It is going to do it again. It's going to call in order traversal again, but there's no node here. So it's going to hit this if not node, and it's going to stop. And then what is it going to do? It's going to do a visit. This is the next thing on the list, is to visit the node. So this is kind of a function. So if we had function visit node, we might just say console.log node.value here. That might be all we want to do. Maybe we want to do something more, But here, just visiting it, it could be anything, right? And then what do we do? Well, it's going to visit the node, and then, and that's gonna print it out. So what does that even mean here? So we're going to visit this. We said if not node, so that didn't work out. So in order traversal returned, we're in green still. In order traversal returned, and now we're going to visit. So where were we? No, I'm sorry. It's going to return empty. I'm so sorry. We're on yellow. We're on yellow right now. Let's go to yellow. So now that in order traversal is done, we're going back to yellow, right? That's here, right here. We still have purple, red, a few reds, and that's it really. And so we're here. We're back on the call stack because we're going back. We didn't finish all these in order traversals. We still had more to go, and there's still more to go in the function. I haven't written it all out yet. Let me write it all out real quick. Right, no dot right. That's it. Right. That's all it goes. So here we are. We're now going to visit it. What's that going to do? Well, this is the number 11. We're going to console log 11. Nice. And then we're going to do in order traversal on node dot right. And so it's going to see if this node has anything to the right. And we're going to use teal. And look, it doesn't. So it's going to get here and it's going to say nope. And then it's going to be done. And yellow is going to be done. So once yellow is done, we got to go back to purple. Because now we can visit because the purple one is finished. It's in order traversal. Now we're back to purple. So it's going to visit the node. It's going to say 3. Then it's going to go in order traversal, node dot right. That's here. That's a 10. Cool. And then here's what's actually going to go on. It's going to say, is there a left node to 10? So let's say there was, right? Let's say that the left node 10 actually did have a left node, right? And it's going to be 30. It's going to visit it first. I'm sorry, it's not going to visit. It's going to call in order traversal on that first. And I'm running out of color. That. Which one's this? Oh my God. Okay. It's a galaxy rainbow color, which is pretty cool, actually. It's going to visit this first, or I mean, it's going to call it first, and then it's going to visit that one. It's going to say 30. That's wicked. And then it's going to be done. And then we go back to 10. And we're back here. Now we're going to visit it. Now we say 10. Or do we actually visit? Oh, now I'm lost. It's kind of difficult, isn't it? I think in order to really nail this down, what I recommend doing is to just build a tree and then check out the input for yourself, check out the output yourself. It's so difficult to go over it just because recursion just throws all this stuff. All right, then there's pre-order traversal, and that's basically when you just swap the visit. So if this is in order traversal, pre-order, you do visit, then pre-order, node dot left, pre-order, node dot right. Cool. And post-order traversal is when you visit at the very end. So you do post-order traversal on node dot left, post-order node dot right, and then visit. Cool. That's important to kind of figure out. So what I recommend doing is pausing this video and running this tree and seeing what you come up with, right? Checking out how it works. And you can see that the presence of the visit at different spots is going to print these numbers out in different orders. And that's what's really important here. So that's what it's all about. Now, next up, it goes into min heaps and max heaps. I recommend these if you're going into more advanced interviews. They're actually super cool, but I'm not going to go over them here. We're actually, I think we're ready to take on tree questions. So I am going to do that real quick. Let me switch over, stop sharing there. And I'm going to actually break this into 2 videos. So I'm gonna do that real quick, and I'll see you in the next one.